Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you need a 4-to-1 balun for a single band antenna. Well, you could go out and buy one, but you don't have to. What I'm going to show you today is a real simple way to accomplish this using just some coax. I'm going to step you through this one step at a time, easy peasy. But not only am I going to show you how to make this, I'm going to tell you why this works. Now, there are some important lessons that are learned through this process, which I will reveal after the final testing. Think of it kind of as experiment debriefing. Be sure to stick around for these important points. If you have questions or comments, please feel free to add a comment to this video. And if you find this video helpful, please click on the like and don't forget to subscribe. My first step is to lay out the design for you. The design is incredibly simple. The only thing that you will need is a piece of coax that is 1/2 wavelength long, which has the same characteristic impedance as your feed line. When I say that it's a 1/2 wavelength long, I mean electrically speaking. I will talk more about this when we get into the actual design of this balun. I'm going to call this 1/2 wavelength piece of coax here the BALUN coax for the sake of brevity. The shield of the feed line and both ends of the BALUN coax are soldered to each other. And then the center conductor of the feed line and the center conductor of one end of our BALUN coax are also connected to one another. And this connection then goes to one side of the antenna feed point. The center conductor of the other end of the BALUN coax gets soldered to the other feed point of your antenna. Now that we can see what the design is made up of, we can better appreciate the explanation of how it does what it does. As I dig into the explanation of how this thing works, the first question that we have to ask is, what sorts of things happen as we travel down a piece of transmission line that is 1/2 wavelength long? Well, there are two things of interest for us in this application, and the first has to do with impedance. Now, if you've watched some of my other videos, you've already heard me say more than once that while the SWR does not change as we move down a lossless feed line, the composition of the impedance which causes this SWR to exist does change. It could start out to be capacitive, and then a 1/4 wavelength later, it will be inductive. The good news is that when we arrive at the 1/2 wavelength distance, we are back to exactly the same impedance composition that we started with. And this is cyclic and predictable using math, or you could use a Smith chart. Now, if you're interested in more information on using Smith charts, you can watch my video series on the subject. I've put a link to that, a first video of the series, up in the corner for you. So I said all of this to come to the place where I can simply say that the impedance at one end of our BALUN coax is the same as the far end of the BALUN coax. So the second has to do with voltage. Now let's take a look at a sine wave. If we start out at the 90-degree point, we have the maximum voltage of the sine wave. Now let's move the 90-degree point over to the 270-degree point. Here we see that we are at the minimum of the sine wave. So if this sine wave were centered around 0 volts and the maximum peak voltage at 90 degrees were 10 volts, then the minimum point at the 270-degree point is minus 10 volts. The difference in voltage between these 2 points would be 20 volts because we're going from the maximum at 90 degrees and the minimum at 270 degrees, and these are 180 degrees apart. Thus, the difference in voltage between the two center conductors of our half wavelength long BALUN coax is twice the applied voltages coming from the transmitter. Now that we have an appreciation for what is happening in our BALUN coax, let's see how all of this applies to the BALUN design. Let's talk about the how. We need to do the math. We have a specific amount of RF power coming to our BALUN from the transmitter, and this does not change. The power is coming in, the power is going out. The power is being delivered to a specific impedance. This gives us the equation of transmit power, P, is equal to the square of the voltage that's on the feed line divided by the impedance over here. In other words, the V squared, the voltage here, squared, divided by the input impedance. This is all to do with our input power. Now, power in, power out, we got the same power here. And the output voltage, as we just discussed a little while ago, is twice the input voltage. So this amount of power is being delivered using 2 times the voltage. So we have 2 times the voltage squared divided by Z out. And we square this and we pull things out. That gives us 4 times the voltage squared divided by Z out. So this is all the output stuff right here. Now, because this power and this power are the same, that means that we can take this equation and this equation and put them equal to one another. Now notice that we have V squared on the top here and we have V squared on the top over here. We can get rid of those by dividing both sides by V squared. So we end up with 1 divided by Z in equals 4 times 1 divided by Z out. Do a little cross multiplication magic, and what do we end up with? The output impedance is equal to 4 times the input impedance. So there you go. Now, let's talk about designing one. The first thing that we have to do is gather some needed information. There are 3 critical pieces of information that we need to design our 4-to-1 BALUN. By the very nature of the design of this BALUN, it is not going to be a wideband device. It is frequency band specific. Thus, the first piece of information that we need is the target frequency of the antenna and BALUN. Now, in order to design this BALUN, we need to cut a piece of coax so that its electrical length is 1/2 wavelength long at the target frequency of the antenna and BALUN. Thus, the second piece of information that we're going to need is the velocity factor of the particular coax that we're planning on using in the design. Lastly, we need to know the speed of light in whatever units that you prefer. It could be feet per second, inches per second, meters per second, centimeters per second, maybe furlongs per second or cubits per second, whatever works for you. We need this with more decimal places than what is generally quoted so that we can get better accuracy in our length. Your choice of units with the speed of light is also going to be your choice of units for measuring the length of your BALUN coax. Now, I've provided the speed of light in inches per second and centimeters per second for your convenience down in the description. So what about this demonstration? What are we going to be doing here? I'm going to design this 4-to-1 BALUN to operate dead in the middle of the amateur radio 2-meter band, which runs from 144 to 148 megahertz. This puts us right at 146 megahertz as our design frequency. For coax, I'm going to be using some RG58 that I have kicking around. This is 50 ohm coax, assuming I have a 200 ohm antenna. If you have a 300 ohm antenna, then you might consider using RG59 or equivalent, which has a characteristic impedance of 75 ohms. Now, apart from this being RG58, I don't know anything about it. So I measured its velocity factor. If you need to measure the velocity factor of your coax, you can reference my series on this subject. I've put a link to the first video in this series up in the corner for you. Using this method, I measured the velocity factor of my coax to be 0.6685. Next, I need to calculate the required physical length of this coax so that its electrical length is 1/2 wavelength of the target frequency. To do this, I used this formula. The physical length of the coax is going to be equal to the speed of light times the velocity factor of the coax, all divided by 2 times the frequency in hertz. Putting all these facts into our equation and using inches for our units, we get a physical length of 27.021 inches or 68.66 centimeters. Now that we have all of our needed information, let's get down to the next planning step. Before we cut anything, we have to talk about configurations. How is this balun going to be connected to the antenna? In my bench experiments, I tried 3 different configurations. Now, all worked, but some worked better than others. The first had pigtails that were part of the balun assembly itself. Both ends of the balun coax and the feed line had 1 3/4 inch or 4.445 centimeter pigtails. The balun coax and the feed line pigtails met at the load. The pigtail at the other end of the balun coax also connected to the load, but this one gave me the poorest performance of the 3. It gave me an SWR of 1.48 to 1 at its best frequency. The second connected everything together with the shortest possible wires. The load connected directly to the short stub of wire which extended out of the balun coax. This one gave me much better performance with a 1.2 to 1 SWR at its best frequency, and furthermore, its best frequency was very, very close to the design frequency of 146 megahertz. The third was the same as the second, except I put a 1 3/4 inch or 4.445 centimeter wires between the output of the balun and the load. Now, surprisingly, this one gave me the best performance with an SWR of 1.1 to 1 at its best frequency. Now, as we saw in the previous video, the addition of the pigtails shifted the frequency of the 3/4 wavelength spot up in frequency. The inclusion of the pigtails in the first and third configuration also shifted the best frequency of the balun up nearly 10 megahertz from the desired frequency to 155 to 156 megahertz. And the good news is that we can compensate for this by making the balun coax longer to shift that sweet spot back down to the desired frequency. So I'm going to choose the third configuration for 2 distinct reasons. First of all, it gave me the best performance of the 3. Second, it gives me a way to adjust that sweet spot frequency without having to recut the coax. Now, as we previously calculated, the ideal length of our coax needs to be 27 1/32 inch or 68.66 centimeters long. Now, let's say that I choose to have pigtails that are 1 3/4 inches or 4.445 centimeters to connect the output of my balun to my antenna. The pigtails are 6.5% of the length of the ideal calculated coax. So I'm going to cut my coax to be 6.5% longer than the ideal calculated length, which gives us 28.79 inches or 78.13 centimeters. While my design is calling for pigtails of 1 3/4 inches or 4.445 centimeters, I'm going to cut my pigtails to 2 1/4 inches or 5.72 centimeters. This way I have room to adjust the sweet spot by trimming the pigtails. Now, with my plans firmly in place, I'm ready to actually cut the pigtails and the coax. So I take my coax and cut it to the desired length, 28.79 inches or 7.13 centimeters. Well, now I need a feed line. I have this fine specimen of a piece of RG58 with a fancy molded B and C on the end. This is what I'm going to use. Now I need pigtails that are 2 1/4 inches or 5.72 centimeters long. What I'm going to do is strip the outer sheath and shield off of the last 4.5 inches or 11.44 centimeters off the end of some more of the same coax. I now cut off the insulated wire that I get and then cut this in half to give myself 2 equal lengths of insulated wire that has the same guts as the coax. Now we get to strip the various pieces of wire and coax. We will strip all of the ends of the coax the same way. We strip off 5/16 inch or 8 millimeters of the outer sheath. Then I trim the exposed shield so that there is only 1/8 of an inch or 3.2 millimeters remaining above the outer sheath. Then I strip the inner conductor to expose 1/8 inch or 3.2 millimeters of the conductor. Well, we also have to strip the pigtails, and I'm going to strip 1/8 inch or 3.2 millimeters off of each end. Using solder paste or flux as necessary, tin all conductors. That's the shields, the center conductors, the whole thing. Now that all my coax is cut to the right length and is stripped and prepared, let's assemble the BALUN. We will need some small bare wire to connect the shields together with. I have some old telephone system wire that I harvested from the dump when the Manitoba telephone folks upgraded the telephone system in Moose Lake. I will use a stripped length of this number 24 gauge wire to connect my shields together. We begin this process by positioning the ends of the coax next to each other. I personally like to position the feed line on the outside and the 2 ends of the BALUN coax next to each other beside it. You might choose to do it differently. I wrap my 24 gauge wire around the shields of the coax in a figure 8 fashion. Using solder paste or flux as needed, I solder this wire to each of the shields. Next, we have to connect the center conductor of the feed line to the center conductor of the BALUN coax. To do this, I bend the center conductor of the feed line at right angles toward the BALUN coax, right at the end of its insulation. Then I bend the center conductor of the BALUN coax at right angles toward the feed line, right at the end of its insulation. Now these should now overlap just a little bit. Solder these 2 wires together. Now we get to add our pigtails to the BALUN assembly. I prepare one of the pigtails to connect to the junction of the feed line and BALUN coax by bending it at right angles as shown here. Then I solder that end to the junction of the feed line and BALUN coax, as you see. Now we solder one end of the other pigtail to the center conductor of the free end of the BALUN coax. The BALUN with its pigtails is complete. The final step in the build is to very, very carefully inspect the entire assembly to be sure that there are no shorts between the remaining strands of the shield wires and any of the center conductors. It only takes one little strand of wire to make things not work right. Now that we have our BALUN built, let's go test it. To test our BALUN, we need to use either an antenna analyzer or a VNA. We will also need a good non-inductive 200 ohm load like this nice 200 ohm metal film resistor. We attach the resistive load to the place where the antenna would be connected. Then we calibrate our VNA and connect the feed line to the VNA or antenna analyzer, and we look where the SWR or return loss is at its lowest point. Using return loss as opposed to SWR will give you a much more definitive reading of the sweet spot of the BALUN. So how did we do? Well, the sweet spot frequency for the BALUN is higher than our design frequency, but this is by design. It sits at 154 megahertz with an SWR of 1.008 to 1. Now that we know that the BALUN is functional, the BALUN has to be weatherized if it will be useful outside. We do not want water getting into things and messing things up. The very nature of the materials we use to weatherize the BALUN will change its tuning somewhat, so we want to do this before we make the final adjustments. Now we get to adjust things to bring this down to where we want it. So how do we adjust this thing? Well, there are two ways that you can do this. The first is with the 200 ohm load that we've already been using. This way we know the BALUN is right and reduces the number of variables that we have to work with. The second is to connect the BALUN to your antenna and adjust it in place. And this has the advantage of matching the BALUN to the antenna, assuming the antenna is tuned properly in the first place. Either way, the process is pretty much the same. The sweet spot for our BALUN was high of the desired design frequency because my pigtails were purposely cut long. So how do we adjust this? Well, we test it for where the sweet spot is. We trim the pigtails off just a little bit, being sure that both of the pigtails are the same length. Test again. Trim a little bit more off of both pigtails. Test again. Trim and test, and you'll see that frequency, that sweet spot frequency coming down. So what are our final test results for this one? Well, the BALUN sweet spot is 146.5 megahertz. It has an SWR of 1.01 to 1. At 144 megahertz, which is the bottom of the 2 meter band, it has an SWR of 1.04 to 1. At the top of the 2 meter band, 148 megahertz, it has an SWR of 1.02 to 1. Now that is pretty doggone awesome. Here are the promised lessons learned. The process worked as theorized, but it needs a little bit of adjustment. My pigtails ended up much shorter than I had designed for. I wanted 1 3/4 inch pigtails. I ended up with 5/8 inch pigtails, which is almost 1/3 the length that I really wanted. This means that the expansion of the length of the BALUN coax wasn't quite sufficient to accommodate the 1 3/4 inch pigtails that I wanted. So how would I adjust this? Well, the desired pigtails were 6.5% of the length of the ideal calculated BALUN coax. So I made the BALUN coax 6.5% longer. Well, if I were to do this again, I would make the BALUN coax maybe 8% longer as opposed to 6.5%. Now, I also noticed that as I trimmed the pigtails, the change per inch in frequency was not linear. You could not predict the next amount to trim off to get your goal. All the more reason to go slow on how much you trim off each time. Now, I was generally taking off about 1/4 of an inch at a time. Be careful to keep the pigtails exactly the same length each time you trim. In the end, I had success and I'm happy with the results. Okay, so my pigtails were shorter than I wanted them to be, but the performance is quite stellar. Now you're ready to build your own 4-to-1 BALUN. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, toodaloots.